In this lecture, we look at a topic that tends to be a bit problematic at first, simply because it is linked directly to a section of work in algebra that you have dealt with and were exposed to since grade 8, and that is exponents. Now, with your exponents, you know what your exponents are. For example, if I say 2 cubed, that simply means 2 multiplied by 2 multiplied by 2. Of course, that gives you 8. If I give you x to the power of 5, well, we know what the fundamental definition of an exponent is. So why do we need something different? Well, I think let's go back to a time when there were no calculators. Suppose you are asked to calculate, correct to 2 decimal places. Let's say a value 5 to the power 0.17, multiply that by 0.18 to the power 9, divide that by a square root of 56.715. Okay, do that calculation, but don't use a calculator. No calculator. Can you do that? Well, I wouldn't say you can't, but it will be quite cumbersome in these days. Now, think back hundreds of years, no calculator. Yet mathematicians, research, be they for chemists, had to work out calculations and values such as these. So what do? They introduced logarithms. And they defined logarithms as follows. The logarithm of a number, y, let's just say y, it could be any variable, is the exponent. So a log is the exponent to which a base, whatever that base is, must be raised in order to equal the number. So let's look at this exponential form. And this is the first thing you're going to do. So we know this is the exponential form. A is the base there. X is the exponent. And y is the number. Then they introduced the log. The logarithm, they said, of the number y, so y came from there, to the base a, that was the base, is equal to that index x. And that is the logarithmic form. And that is the first thing you must be able to do, to convert from exponential to log and log to exponential. So look at that carefully. Your exponential form, a to the x equal to y. What's the corresponding logarithmic form? While we use the abbreviation log, there's the number y. We put the base, whatever that base is there, to the base a is equal to that index, whatever that index there is, x. So you convert from exponential to log and vice versa. You must be able to do it in both ways, from log to exponential, from exponential to log. That is the first thing that you have to do, conversion. But before we look at the actual conversion, let's just highlight a very, very important, and I'll use that highlight, that's what I was looking for. The base A must be greater than 0. I'm looking for a highlighter. What did I choose? Highlighter. The base A must be greater than 0. So with the mathematics and with the concept that we deal with here, that base, we're always going to take a positive base. We could take a decimal. We could have a fractional base. Like that A could be a half, that A could be 0.5. Yes, that's fine. However, we must choose a positive base. A must not equal 1. Now imagine if I choose A to be equal to 1. Let's say this A here is 1. Now that 1, if that is the base, oh, have I chosen the same color? If I choose a base 1, irrespective of what index I put there, what's 1 to the power 10? It is 1. What's 1 to the power minus 0.5? What's your answer? 1. It's 1 irrespective of what index is. So that is the reason. That means we'll always get 1 as an answer. The number, the answer, we won't be able to convert to log. But there is a property that we'll come across at a later stage. So A cannot be equal to 1. That's the first thing. While the second, A must be greater than 0. The base A must be positive. And then thirdly, extremely important, once again, what am I doing? I'm looking for the highlighter. The Y will always be positive. Now, let's consider that again. Why do I say that that Y is positive? So where does the Y come from? That's the Y over there. Look at this. If I take 5 cubed, what's my answer? 125. If I take a half squared, what's my answer? That's right, a quarter. Irrespective of what base I choose, I will always get a positive answer. So that answer that you get there will always be positive. And that's the Y that I'm talking about here. That Y over there. And if that's in the exponential form, in the logarithmic form, that Y there must always be greater and will always be greater than 0. Okay, let's remove some of these, make it a little neater per se. So I'm going to take all these away and again look at the very important aspect of converting from exponential to logarithmic and logarithmic to exponential. So when we have a base A to a power x, it's equal to the number y. I can convert that to logarithmic form. It becomes the log of the number y to the base A equal to the index. And here I have some form, some examples. So let's take an exponential form, convert to logarithmic form. 3 to the power 4 is equal to 81. What's the base? 3. What's the index? What's the number? What's the corresponding log form? The log of the number to the base 3 is equal to the index 4. Now I'm using the terminology log of a number 81 to the base 3. Sometimes teachers or lecturers will say log base 3 to 81, or they may use some or other form of notation or their way of description of a log. I'm sticking with this. Let's look at number 2. The base 2 to the minus 3 is equal to the number 1 over 8. Therefore, the logarithmic form is the log of the number 1 over 8 to what base? To the base 2 is equal to the index minus 3. If you have to convert to logarithmic form, to exponential form, sorry, we have log 125 to the base 5, that's equal to 3. So what's the base? The base is 5, there's the base. This is the index 3 is equal to the number 125. Convert log y to the base x equal to t to exponential form, x to the index t is equal to y. And with that in mind, we can actually write down answers such as this. What is the log of 4 to the base 2? Think carefully. Well, it should be straightforward because that's the base. This is the number that it will be equal to, and what you put here must be the index. So if that's the base 2, I need to put the index here to equal to 4. What's the index I have to put? 2. So that's equal to 2. You do this one. What is the log of 1 over 27 to the base 3? What's your answer? Think carefully. That's right. Minus 3, because 3 to the minus 3 is equal to 1 over 27. Now look at this. This is something that you may come across many, many times. What is the log of 7 to the base 7? Answer? That's right. As long as that and the base is the same, your answer is 1. Now we get to a very important thing as well. What is the log of 1 to the base 3? 3 to what power gives you 1? 0. Log of 1 is equal to 0. And those are properties that you will come across all the time. Okay. Now, 2 bases are used most of the time. The one that if you did logarithms in school in depth, the one with the base 10. So if I have log of x to the base 10, when you have a base 10, normally it's not written. So when you see log of x, that is understood to be base 10. So if I say log of 3.14, what is the base understood to be? It's understood to be 10. We don't have to write it out. What is the log of x? The base is understood to be 10. Whenever a log appears without its base, it's understood to be the value 10. Now, secondly, and this is something you might not have come across before, the natural base e. Now, e is a value that appears quite often in physics and science and is used extensively. And the value of e can be found in a number of ways. I've used a basic calculus definition where the limit as n tends to infinity of 1 over 1 plus n to the power n. Now, I'm not going to go through with that, but in essence, e is approximately equal to 2.718281828. So whenever you see e in mathematics, you can say that is approximately 2.718. Now, the log of a number having a base e is known as what we call a natural log. And when you see log of x to the base e, it's written as ln of x. So if you see ln of 5, then that is a base that's understood to be e. We should actually write log of 5 to the base e, but we don't. We reduce it and we simply write log 5. So you're going to come across this many times. Ln of t, ln of x, and so on. Ln of 2x minus 1. So those are the bases that we are going to come across quite often. The normal or standard log with the base 10, which is not written down, and then the natural base with the base e. Now, I think just before we go on to the laws of logs, there's something that I want to make sure you understand. The introduction and the definition of logarithms. Look carefully at the definition. It's the log of the number y to a base a, and that will be equal to something. Now, why am I pausing here? Because I just want to see whether you are going to get and understand that if I do that, what is that? That is nothing more than a word called log. In mathematics, it has absolutely no meaning. And with this in mind, I also ask you to look at that. If you tell me now that that is sine in mathematics, then I can tell you your understanding of trigonometry leaves a lot to be desired. Because look at it, it's a sin to do that in mathematics. You can't do that. It doesn't make any sense. It has to operate on something. So if it's a sine, it is a sine of an angle that you can replace by some value. Sine of 30, sine of 60. And you've worked on special angles at school. You know what those answers are. But if you just write that, then it is a sin to do that in mathematics. Likewise with log. It has to be followed with the number. Then that can be replaced by a particular value. For example, the log of 125 to a base 5. Yes, that entire thing can be replaced by the value. Exactly. So if I say, what is 7 log of 125 to the base 5, then you can say that 7 multiplied by 3, that gives you 21. But if you just write log, then I just write 0. If you write sin, then you know where I tell you to go? 0. So be careful. Okay, let's look at some laws of logs. The most important are these. So firstly, number 1, the log of AB to a base k. The log of AB, and I've chosen a base k. Remember, that could be any base. And that is a log of a product that contains a number of factors. Now, I'm going to emphasize this because this laws of logarithms are extremely important. I'm going to take some time to ensure that you don't make the fundamental errors that many students make when they first come across logarithms. So that must be a product and composed of factors. Now, in this case, there's 2 factors, A and B. A and B. And that can be separated into the log of the first factor A to the base k plus the log of the second factor b to the base k. So for example, if I give you log of x times y is a product, there's two factors, then I can separate that because that's the standard logarithm to the base 10. I can say that is the log of the first factor x plus the log of the second factor y. Let's do more examples of that. And that can be expanded. Log, let's say, to the base 7 of 5 a squared b cubed d. Now look at that carefully. That is our base 7. And how many factors do you have there? 1, 2, 3, 4. So I can separate those into the log of the first factor 5 to the base, then plus the log of the second factor a squared to the same base, and I can continue. There's plus the log of b cubed to the base 7 plus the log of d to the base 7. And of course that applies to ln. That applies to ln as well. So I have the ln of, let's say, 3x y to the power 5. There's 1, 2, 3 factors. So it's a ln of the first factor plus the ln of the second factor plus the ln of the third factor. Ln of y to the power 5. That's your logarithmic laws. Now, we should be proving the log laws, but I'm not going to. It would be extremely useful and also mathematically powerful to see the proofs of these laws. You can look it up. You can look at all the textbooks that are available. The proofs are there, and I advise you to do that as well because it gives you deeper insight into the definition of the log. Now, I can apply that to the second one. The log of a fraction, let's look at the second, to the base is the log of the numerator minus the log of the denominator. Remember, the first one was a product. The second one is division. So the log of x over y is equal to the log of the numerator minus the log of the denominator. Let's expand that now. The log of, and of course that numerator and denominator could be anything. For example, it could be 2x minus 7 divided by x plus 10. The numerator is 2x minus 7. So I get the log of the numerator minus the log of the denominator, x plus 10. Now, I just want you to be careful because I'm going to bring this up right now. People get tempted. What is the temptation? The log of a plus b. Look carefully at the laws. There's no law on that. There's nothing you can do. The first law is the log of a product. Inside the brackets is not a product. Now, if you look at 3 times a plus b, yes, you are taking a number and you're distributing into the bracket. You're taking a number and you're multiplying by the variable. So it'll be 3a plus 3b. But you cannot do it here because this is not a number. If you separate, if you decide, let me multiply log by a, that means you're taking a word and multiplying it by a variable. That doesn't make sense at all. So what can you do with that? Absolutely nothing. You just have to leave it as log of a plus b. Please remember these because these are temptations and the fundamental errors that are made by students. Now let's combine. Look at this one. Let's separate the log of, let's say, 5xy divided by AB. Now, first using the numerator and denominator, I get, and using log law 2, I get the log of 5xy, numerator, minus the log, denominator, AB. But this is a product with 3 factors, and this is a product with 2 factors. So I can now separate that. The log of 5 plus the log of x plus the log of y minus, but now I must open brackets. And the log of AB is the log of A plus the log of B. And when I remove those brackets here with the negative, they will become, if I could just rewrite it, I would want to try and write it on the same page so that we don't have, can I just remove this? So I can write it all up here and say log of 5 plus log of x plus log of y minus log of A minus log of B. So there I have now separated the log of a complex fraction into separate logarithms with definite signs. The positive signs came from the numerator, the negative signs from the denominator. So let's look at another example. Let's take this one. And here I want to write as separate logs. So I have the log, or let's do this. Let's rather use the ln. The ln of the fraction 7a squared b cubed divided by x square root y. Now I want to write that as separate logarithms. It would be useful, and many times it's placed in brackets. So in the numerator, those are all factors. They must all have a positive sign. It will be the ln of 7, because 7 is a number and it's a factor by itself. So don't group it together with the a squared, separate it. So it's a ln of 7 plus the ln of a squared. Yes, what's the next one? Write it down. That's right. Plus the ln of b cubed. Now x is in the denominator, so what sign will that get? Minus the ln of y. Sorry, the ln of x. Let's just take that. We all make mistakes, eh? But we must correct it immediately. And then the square root of y is in the denominator. And as I showed previously, whatever factor is in the denominator gets a negative sign, so it's a ln of the square root of y. All separate logarithms. Nothing you can do further at this stage. Okay, let's go on to the next law, which is the log of a exponent. The log of a to the power t all to the base k. And that can be written as t log of t. No, sorry, that should be a to the base k. Now, what is extremely important here is that the a has the index t. So a has the index t, and then only can I bring t to the front. Okay, let's go on to the next page and I will do it the third law. So the third law states this. Maybe I'll use different letters. Yeah, let's use different letters. Log of x to the base t. Okay, that's understood to be the base 10. X is raised, so it's x that is raised to the power t. X is raised to the power t. And when x is raised to the power t, so let me take this away, then that t can go to the front. That t can go to the front, so I can take this t all the way to the front, and that becomes t log of x. So for example, if I say log of y cubed, how can I write that? 3 log of y. Yes, I can go on and on and on. What is the ln of t to the power 0.5? Yes, 0.5 ln of t. You tell me quickly, what is the ln of the square root of y? While I start erasing. Yes, you should have an answer already, don't you think so? Yes, I can write square root of y as y to what power? That's ln of y to the power half. And now I can take that half to the front, half ln of y. So what is the log of the cube root of a? Yes, can we write it immediately? Because that's a to the power 1, 1/3 log of a. So these three laws form the crux and the basis of logarithms. You need to know them thoroughly. And once again, the first thing that you must be able to do is take a complicated logarithm and separate it. So let's see, I got log of 8, a cubed, square root of b, divide that by x to the power t, y to the power 4. Write that as separate logarithms. So combining all three, 8 is the factor, a cubed the factor, square root of b. But square root of b I can write as b to what power? To the power half. I can separate that and they'll all have positive signs because they're all factors in the numerator. And in the denominator, both x and y will have negative signs. So I'll do this in 2 steps, but you don't have to. Log of 8 must be by, even though it's a number, separate it. Make it sure you write it as a separate log. Take 8 as a factor. Don't group 8 and a cubed. 8 must be by itself. Log of 8 plus the next factor, a cubed, plus the next factor, b, and I'm going to write to the power half. Then what's the next sign? Minus the log of x to the power t, then minus the log of y to the power 4. And now I can use the third law of log of 8, 3 log of a half log of b. Why? What am I doing? That's third law. I can apply the third law. I can apply the third law. Minus t log of x minus 4 log of y. There you go. Now, this particular step, when you get used to it, you don't need to write that. You can just write this answer immediately. And before we go on to the reverse process, look at this carefully. The ln of sine cubed x times x plus y squared, divide that by the square root of tan x, and 7 times the square root of tan x. Yes. What do I want you to do there? Write as separate logs. Now I'm going to write the answer immediately. And I want you to think carefully but how the answers are obtained. Okay, let's try the first one. Write down your answer. Let me see. Write down your complete answer. I'll give you a few seconds. So what are you doing? You're writing as separate logarithms. Okay, because this is a video, I'm going to give you the answer. Ln sine x, but sine of x is cubed. So that will be 3 ln sine of x plus ln of x plus y, and that's x plus y squared. The 2 comes to the front. 2 ln of x plus y minus the ln of 7, and square root of tan x is in the denominator, so it's minus square root is a half ln of tan of x. There you go. Did you get that right? 3 ln sine of x plus 2 ln of x plus y minus ln of 7 minus a half ln tan x. Do we stop there? Who said no? Can we simplify further? Absolutely not. We stop there. Were you tempted again? Ln of xy, can you do anything with ln of x plus y? No, you can't. So we leave that as your answer. Now, I'm going to go to the special cases before no, well, we've done the special cases. The reverse of this. In other words, I want you to write a list of logarithms as a single log. So for example, if I give you 2 log of x plus 3 log of y minus 4 log of z, can you now combine it in the reverse process? So what we are actually doing, if we have to go to our properties, we're going to do the reverse process. When we have the sum of logs, we're going to write it as a log of a product. When we have difference of logs, we're going to write it as a quotient. When we have the index t, we're going to write the reverse process like that. So let's have a look at that example. Do you think you can write that as a single log? In other words, the log of what single fraction here can be separated into that answer? Well, all we do is just look at the signs. There's a plus, there's a plus, there's a minus, so we must have a fraction. Whatever plus is, then that's the base, and that 2 goes to the top, and that will be in the numerator x squared. That's a plus, so it'll be times. Very important. Remember, when you have plus, 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 it came from a product, so they were factors. And then the 3 goes to the y, so that will be times the y cubed. And the minus, that means that z must go into the base, z, and that becomes z to the power 4. Now, don't make the mistake of putting z at the bottom and writing minus 4. This minus tells us that this term here is in the denominator. It must go into the denominator. So we use the minus sign to tell us where to go to. Then I use the plus 4. Then I use the 4 to go to the index. And you can check that out. So here we can write as single logarithms. What about this? I have a half of the ln of cos of x minus 3 ln of x plus 2 ln of, let's say, 2xy minus 1. Now, before I actually do this, I want you to look very carefully. I can write as a single log, provided all the bases are the same. So these all, in the first case, these all have log 10 as a base. The base is 10. It's a standard logarithm. In the second case, I've got ln, so the base is e, the base is e, the base is e. Oh, sorry, I had a 1 here. But this is a 1. There's no ln over there. So I could write these first 3. I can combine, but then minus 1 will be out completely. But I don't want that. I want to combine all of them into 1. Into a ln of 1 fraction. That means I must take this 1. So let's write the 1 here. And I must write it as a ln. Now the ln of what gives you 1? Remember, ln has a base? Yes, the base is e. So it's ln of e. The ln of e is equal to 1. So I can replace this 1 by ln of e, and I'm going to do that. That will be a half of the ln of cos of x minus 3 ln of x plus 2 ln of 2xy minus the ln of e. Because what is the ln of e? The ln of e is 1, and that is a property you must not forget. Ln of e is equal to 1. Now I can write as a single log. Of course, it will be ln in this case. This will be that's a plus, so that must go in the numerator. That's a minus, that must go in the denominator. That's a plus, goes in the numerator. That's a minus, goes in the denominator. But because it's a half, so I'm going to write square root of cos x. Are you happy about that? Cos x all to the power half is the square root. The 3 goes to the x, and that's x cubed. Because of the minus sign, goes into the denominator. Then the 2xy, so this will be multiplied by 2xy, and that's the entire thing. So when this goes to the index, it goes to the index of that whole bracket squared. And then minus sign, that means this e must go down into the denominator. And there's your single logarithm. If you want to write it in another way where I just have to square all of these, and I can square because this is all multiplication, I'll get 4x squared y squared square root of cos x, divide that by x cubed, and of course I can simplify further. The ln of 4y squared square root of cos x, the x squared and the x cubed, ex, and there I've written as a single logarithm. Yes, this may be ln, but it's still logs with the base e. Okay, now some very important cases which I have already mentioned, but I'm just going to emphasize here. I've also mentioned the errors. So in the first one, log of 1 to the base k equal to 0. Irrespective, ln of 1, 0. Doesn't matter what the base is. What is the log of 1 to the base 1/3? Answer, 0. Irrespective of what the base is, your answer is 0. Ln of 1, 0. What is 5 ln of 1 plus 3 log of 1 to the base 0.7 minus 1 divide that by, or log of 1 divide that by a square root of x. What's your answer? What's ln of 1? 0. What's the log of 1? Doesn't matter what the base is. 0. What is the log of 1? 0. What's your final answer? 0. Now look at that very carefully, because I did not separate ln and 1. I said ln of 1, or the log of 1, not log. Log of 1. The log of 1, ln of 1 is equal to 0. The next property, the ln of t, or the log of any number with the same base will always be equal to, remember the answer you put on the right hand side of this equal to sign must be the index. That's the base. 7 to what power gives you 7? 1. Log of 7 to the base 7? 1. What is the log of 3/4 and the base is 3/4? Your answer is 1. So what is 7 times the log of t to the base t minus 3 ln of e plus 5 log of 0.9 to the base 0.9. Work that out. What's log of t to the base t? That's the property. That is 1. What is the ln of e? Ln of e is equal to 1. Remember, oh, sorry about that. The ln e, what's the base? Answer 1, but you don't put that. Ln of e is 1, so that will be 3 times 1. What's the log of 9? 0.9 to the base 0.9 plus my 5. Can I add 7 minus 1? It's an equal to sign. Okay, let's just put it over here. 7 minus 3, 4, 4 plus 5, 9. I've already, looking at some common errors, I've already emphasized you can't simplify that. And this one, oh, that is a very, very common error. What is the ln of 8 divided by the ln of 16? You know, I don't know how to emphasize the understanding. Can I cancel out that ln with that ln? Okay. What is the sine of 30 degrees divided by the sine of 60 degrees? Can you cancel out sin? That's exactly what you're committing. You're committing a sin if you do that. That means you have not understood what sine is and what ln is. So be careful. Don't you ever cancel. And why do people cancel? Because it's so easy. It's so tempting on the eye. You've done it so many times in the past. You know, when you got, oh yeah, cancel x and x, 2 goes into 4, so your answer. You've done it so many times before in the past. That's why you tend to, but now I'm emphasizing, I am highlighting, there you go. I am trying to force you to think logically and conceptually. So when you have ln of 8 over ln of 16, you can't cancel out the lns, you can't cancel out the 16s. But what you can do, oh, I have it here. You can write this as the ln of 2 cubed over the ln of 2 to the power 4. Then you can apply the third law. The 3 can come to the front, so it's 3 ln of 2 over 4 ln of 2. And now when you cancel out, you're canceling out the entire ln of 2. So your answer is 3 over 4. Right, now with that in mind, let's go on to log laws and definitions. We've already discussed this. writing as separate logarithms. We've already discussed this, write as a single logarithm. So now we're going to use these concepts, these laws of logarithms to solve logarithmic equations. Right, and there are a number of sort of processes and properties that we can use to solve logarithmic equations. Are also important, and something that I want you to look at all the time is the restrictions. Now, I'm just going to go back to the first slide just to remind us what were the restrictions. The restrictions came here. The base must be greater than 0. The base must not be equal to 1. And this part here, the log of that, whatever you see over there, when you see the word log, when you see that operator log or ln, whatever it's acting on, that y part must always be greater than 0. And that restricts your answers when you get to logarithmic equations. So that part is the restriction. And I'm going to write the restriction down immediately. Whatever follows on log, which is 2x plus 7, that must be greater than 0, which means x must be greater than negative 7 divided by 2. Now I must keep that in mind. That restricts my answer. Now, I could do the restriction first, then the sum, or I could do the sum first, then the restriction. I'm not going to stick to any particular procedure. You'll see as we go along. So the first one is exponential and logarithmic form. In other words, the definition. And we already discussed the definition. That's the exponent. That's the base, sorry. That's your base. That's the index. And that is your number. So this is logarithmic form. This is log form. Now I'm going to convert to exponential form. The base is a half. The index is -5. And that will be equal to the number 2x plus 7. Now we simply solve this as an exponential equation. A half, so this is schoolwork, 2 to the -1 is a half, to the -5 equal to 2x plus 7, -1 times -5, that's plus 5, is equal to 2x plus 7. What's 2 to the power 5? Oh, you take your calculators out, 2 times 2 times 2 times 2, yeah, 32 is equal to 2x plus 7. Transpose, work it out, you know what to do after this. That's 25, x is equal to 25, divide by 2. And there's my answer, but now I must just double check. Is 25 over 2 greater than -7 over 2? Yes. So I accept this is my answer. So that's essentially the first type that you come across, where you given an equation. It could be in basic definition log form and you convert to exponential form, or you give an exponential form, convert to log form, and then solve. But for this particular example, most cases, if it's a log of something equal to some right-hand side that doesn't have a log, you can convert to exponential form immediately and solve. Now, the second case is what we call log equivalence. Now, what do I mean by log equivalence? Look at this. If I say the log of x to the base 7 is equal to the log of, let's say, 3 to the base 7. Look at those very carefully. The log of x, the base is 7. This log is acting on x, and the base is 7. And on the right-hand side, you also only have logarithm once, and the base is also 7, and it's acting on 3. That means x in this case, therefore, x can only be 3, nothing else. Now, be careful. I did not say cancel off log and base 7, because in effect, that is not the concept that you're applying. You are applying what we call log equivalence. Provided the bases on the left-hand side is equal to the base on the right-hand side, then the argument, what is the argument? This part here, that part there. The arguments are equal provided the bases are equal. But very important, you must have log once on the right-hand side and log once on the left-hand side. So let's look at our example here. I've got all base 6s, that's true, but I've got log there, and log there. I can't use log equivalence right now. Do be careful. Some people, of course, are tempted. Just let me cancel a log 6. Oh, the log and the 6, cancel. It makes it so easy. It's wrong. You can't do that. So what do you have to do? That's why we went through combining logs, writing as a single log. So let's look at the left-hand side. I've got a plus sign and a minus sign. And the log is the base 6, so it will be a fraction. The one with the plus sign, which is x plus 1, goes to the numerator. And the one with the negative sign, which is 4x plus 10, goes to the denominator. And that will be equal to the log of 1 over x to the base 6. Now it looks like this. Now I can say log is acting on that fraction, log is acting on that, and the base 6 and the base 6 is the same. Therefore, that x plus 1 over 4x plus 10 must be equal to 1 over x. There you go. And now I can solve this. Now I can solve it, just like we did in school. Now, because I have one fraction on the right-hand side and one fraction on the left-hand side, I can do cross multiplication. So I get, or if you want to do the long way, you can multiply by the LCD x times 4x plus 10. You're still going to get this answer, x times x plus 1 is equal to 4x plus 10. Okay, the rest is going to be straightforward now, where you're multiplying out, you're transposing, and you are simplifying. I don't need to use the quadratic formula in this case because you can factorize. And then I'm going to get my two answers, 5 or x equal to minus 2. Now, these are school processes and procedures. So you should know how to do that, and you can go through that yourself. However, what didn't I do? My restrictions. Where did the restrictions come from? From there. X plus 1 must be greater than 0, which means x must be greater than minus 1. That's the first case. And there, for x plus 10 must be greater than 0. X must be greater than minus 10 over 4. And then this is also a restriction. The denominator cannot be 0. So now, against every single one of those restrictions, take minus 2. Is minus 2 greater than minus 1? No. So x cannot be equal to minus 2. Neither is it greater than minus 10 over 4. What about 5? Is 5 greater than minus 1? Yes. Is it greater than minus 10 over 4? Of course, because 5 is positive. Therefore, the only answer is x equal to 5. Log equivalence. Let's go to the next one. Another example over here. Also log equivalence, but we're using ln. But then I noticed that this 2 doesn't have a ln. Now, can I introduce a ln? Well, what I normally do is very easy. I say 2 times 1 is 2. but one ln is ln of e. So I can write that, taking that to the top, ln of e squared. This is where you must know your properties thoroughly. So now I can say, okay, I can write that as ln of 2x plus the ln of 3x minus e minus the ln of e squared is equal to the ln of 8. There's 1, 2, 3 logs. I must write this as a single log now. That has a plus sign, that has a plus sign, that has a minus sign. So it'll be 2x times 3x minus e, divide that by e squared is equal to ln of 8. Writing as single logs. Now it satisfies my property. There's ln on one side acting on the bracket. There's ln on the other side acting on 8. Therefore, this bracket, 2x times 3x minus e divided by e squared is equal to 8. And now I can just multiply out 2x times 3x, 6x squared, 2x times minus e, 2x e, and then cross here 8e squared. Now, to solve this, we are not going to use the value of e. I'm going to use a trinomial. Firstly, I'm going to divide by 2 and transpose the 8. So if I divide 6 by 2, I get 3x squared. If I divide 2 by 2, I get xe. If I divide 8 by 2, I get 4. And then transpose that, I get minus 4e squared equal to 0. Now this is actually a trinomial. If you recall trinomials, for example, x squared minus 2x minus, let's say, 3. If that is a y, I could put a y squared here. And then that can be factorized. Except my variables, the first will be a x, and the second of the bracket will be a y. So it'll be x and y. And then the factors of 3 is 1 and 3, so I can write this as minus y minus 3y, and of course that will become a plus. So look at the variables there, coming from the x squared and the y squared, and putting that in brackets, the first will be x, the second will be y. So I'm going to do likewise over here. It will be a x and what? That's right. It will be x and e. And then find the factors. Will be 3x minus 4e and x plus e. Therefore, 3x minus 4e is equal to 0, or x plus e is equal to 0. In this case, I'm going to have x in terms of e. So x will be equal to 4 over 3e. X will be equal to minus e. What do we still have to do? Restriction. What's the first restriction? 2x greater than 0. Divide by 2, x must be greater than 0, which immediately cancels off this because this is a negative value. This is x greater than 0, so x cannot be equal to minus e. What about the next one? 3x minus e greater than 0. Transpose the e, divide e over 3. That's e over 3, and this is 4 over 3e, so I will accept that as the answer. Now notice here, I did not write down the value of e. In many, many instances, we leave an answer with e instead of writing on its actual value. So get used to that. Right, and then the next one is where we actually introduce logarithms. Now, where is this used? Do you remember when you did finance, mathematics, and you're doing compound interest, and you came across something of this nature, and the lecturer or your teacher just told you, okay, just write down your answer, log 23 over log of 5. Do you recall that? Well, why was that? Because you actually introduce logs on both sides. Now, why would you introduce logs? Because it will be the case. If this was 2x equal to 8, then you'll say, oh, that's so easy. Therefore, x is equal to 3. Yeah, but now, yeah, is not a perfect power of 5. That's when we introduce logs, and then the x comes to the front. X log of 5 is equal to the log of 23. Sorry, 23. Now I divide by log of 5, and x is equal to log of 23 divide by log of 5, and there, yes, you can use your calculator. And don't come and cancel logs. That's why I prefer you put it in brackets. So here we introduce logarithms. However, before you introduce logarithms, I want you to isolate the index. So what do I mean? See that part there, that's 2 times, right? I want that to be by itself on the left-hand side before I introduce logs. So first we're going to transpose. That's 2 multiplied by 5 to the 4x plus 3. Transpose the 12. That will become 20. Now divide by my 2. 5 to the 4x plus 3 is equal to 10. And now I can introduce logs. And you can introduce logs or you can introduce ln. I'm going to introduce ln of 5 to the 4x plus 3 is equal to ln of 10. Now look very carefully. That becomes an entire bracket. That entire bracket goes to the front because that's the whole index is equal to ln of 10. And then I can divide by the ln of 5 because now I want to find my x. I'll get the ln of 10 divided by the ln of 5, and then the rest is normal. Transpose ln of 10 over ln of 5, subtract 3, and divide that entire thing by 4. I'll get ln of 10 over the ln of 5 minus 3 divide by 4. You can write it any other way. I think I've worked this out correct to 2 decimal places to 0, negative 0.39. So that's introducing logarithms. The last case is when we use the definition. But we use the definition of a logarithm, however, using the natural log. So yeah, we know that ln has the base e, and that is the index. So we can immediately say e to the negative 0.6931. Now look carefully at that. Solve for x, and I've given you, so I brought trigonometry into logarithms, is equal to sine of x. Now I'm just going to write it the other way. Sine of x, and I'm going to calculate that, and that gives me approximately 0.5, correct to 1 decimal place. And then how do you do that? Arc sine of 0.5, and it's positive, so it's plus 0.5, so it's in the first quadrant 30 degrees, or in the second quadrant 180 minus 30. Therefore my answer 30 degrees or 150 degrees. So now using logarithms, generating trigonometric equations and using the definition of the natural log. combination, combining. Our last examples, 3 divided by 1 plus e to the power 2x is equal to 2. And I want to solve for x. The only way is to try and bring this x down, but I can't, I cannot, and you should not introduce logs at this stage. You must first isolate that exponent. So I want that e to the 2x to be by itself. So how can I do that? By manipulating, cross multiply. So that will be 3 is equal to 2 times 1 plus e to the 2x. Still not by itself. Multiply, I'm going to multiply by 2, yeah? 2 plus 2 times e to the 2x. Then we're going to transpose. 1 is equal to 2 times e to the 2x. Notice what I'm doing. I'm trying to get this all by itself on the one side. And now I can divide, and it doesn't matter which side. I'm going to write it on the right-hand side. E to the 2x, 1 divided by 2. Now I've isolated the index. Now I can introduce. And we introduce ln in this case. Why? Because the base is e. So it'll be the ln of e to the 2x is equal to ln of half. You know what happens next. And tell me, what is ln of e? That's 1. 2x is equal to ln of half. X is equal to, divide by 2. I'm going to write that as a half ln of a half, which of course I can write as the ln of the square root of a half. You must be able to make these connections. Why is that so? Because that half can come to the top there. It becomes ln of half all to the power half, which is of the square root. Now, that completes this particular lecture. What is important is that you go through this video again and I just need to go through this video and look at the notes, because the examples in the notes are different to the examples that I've discussed here. A lengthy but necessary, absolutely necessary recording. So cut down into 2. First do 50 minutes and then another, say 30 minutes and then another 30 minutes.